Hello, everyone. My name is Tianyi Ouyang. I'm from University of California, Riverside, in Joshua Lewis Group. Today, my talk is about tunable gamma and K-valley exciton polarons and correlated states in trilayer tungsten disinolite. So first, let me briefly introduce the K and gamma valleys in transition metal ditrichalconite, which is called TMD. And in my talk, I only focus on the WSe2. And this is a crystal structure of monolayer WSe2. And this is a Brillouin zoom with K values are on the corners and gamma value on the center. And this is a band structure of monolayer WSe2. And if we calculate the effective mass of K value, and we can see we can get 0.4 times electron mass. And then if we get the effective mass of gamma valley, we can get a much larger value. And also we can see that gamma valley is flatter than K valley. This is actually our motivation. So heavy gamma effective mass can generate very different many-body physics. So in my talk, I will talk about two aspects. First, I talk about exciton polaron formation, and in the second part, I will talk about charge correlations. And then let me briefly introduce the formation of exciton polarons. Uh, so we just take monolayer TMD as an example. For monolayer TMD, we have K and K prime values. If we inject a light, we're going to create an exciton in K valley. And at the same time, if we dope the system with free carriers, we're going to form a Fermi C also in the K valley. And then the Fermi C can interact with exciton to form this KK exciton polaron. So if we measure the reflection contrast map of monolayer WSe2, we're going to get the exciton polarons, and this is corresponding to the KK exciton polaron. And then if we talk about multi-layer TMD, on the valence band side, the gamma valley always dominant. And if we dope the system, we dope gamma valley as well. And this gamma valley Fermi C can also interact with the KK exciton to form this K gamma exciton polaron. So it means that gamma valley can give rise to the additional formation of exciton polaron. Based on this idea, we need to find a platform to study this K gamma exciton polaron. And here we find trilayer WSe2 is a very good platform to study K and gamma valley exciton polarons. This is because it has electric field switchable K gamma valleys. So this is the band structure of trilayer WSe2, and y-axis is energy, and the x-axis is momentum. And if we zoom in this part, we're going to see that uh, the red line is corresponding to zero electric field, and dashed lines are large finite electric field. So we can see that at zero field, K value is lower than gamma value. And if we apply a strong electric field, the K value will be split into three branches, and one of the branch is higher than gamma value. And this can be illustrated by this simple cartoon. So we can see that at zero field, K value is lower, and then at strong field, K value will be lifted and higher than gamma value. So based on this idea, we just fabricate our device. This is a simple schematic of our device with BN encapsulated and graphite contacted and gated. With this dual gate structure, we can independently control the doping density and electric field in our sample. And then we just measure the reflection contrast of our device. So we can see that this is our data with first derivative. And in the middle is our neutral exciton, and upper is electron injection site, and lower is hole injection site. In our study, we only focus on the hole injection site, and we can see there are two signatures. One is strong and the other is weak, and we just attribute these two features into K gamma exciton polarons. This is because at zero electric field, gamma value is higher, and we dope the system. We just dope gamma value first, and then the K gamma exciton polaron can be formed. And this formation of K gamma exciton polaron is pretty weak, and the binding energy is around 4 millieV. So it means that this binding is actually extremely weak. And then if we apply strong electric field, we're going to lift up K-values. And then we measure the reflection contrast again, we're going to get a very different result. So here we still focus on the whole injection side, and we look at this high doping regime first. And in this case, we still attribute the features to K-gamma exciton polaron. So this is because the gamma valley is doped in this case, and K-gamma exciton polaron can still form because of the large size of Fermi-C, but the K-valley behavior are suppressed. This is because of some state fielding effect. And if we look at this small doping regime, we can see that the feature is very different. And in this case, the exciton can interact with K-valley Fermi-C to form this KK exciton polaron. And this binding is actually much larger, which is around 15 millieV. This is very similar to the binding energy of trions in monolayer WSe2 case. And then if we apply intermediate electric field close to the transition point, we can get an intermediate state uh, of the reflection contrast result. And here we look at the yellow arrow, and we can get this band alignment. In this case, we have a higher gamma valley, uh, and this feature is still attributed to K gamma exciton polaron. And then if we look at this point, we can see that this feature is actually distorted. This is because the lower K valley is doped, and you have extra Fermi-C close to the gamma valley Fermi-C. So that's why this K gamma exciton polaron is just distorted. And then if we look at this king point, which is labeled by this yellow star, this is corresponding to a critical case that the gamma valley is doped, and it just starts doping the lower K valley. So this is a critical case. And then if we change the electric field, we can see this kink point is just increasing, and finally it reaches a very special case that K valley and gamma valley has same energy level. And then if we keep increasing the electric field, we are going to see that the K value will be higher uh, than gamma valley. So in this case, we can see that a very different feature. This is corresponding to KK exciton polaron. So based on this idea, we can think about uh, the K gamma valley switchable correlated states. And this part of work is mainly done by Aoshi in our group, which is related to tunable K and gamma valley correlated states in trilayer WSe2 Moiré superlattice. And based on this idea, I just briefly introduce the background. This is a simplified lattice structure of trilayer WSe2. If we have another perturbation layer of for example, like a monolayer WS2, and we put the trilayer WSe2 on top of the monolayer WS2, we can form Moiré pattern. And based on this case, if we dope the system by holes, for example, like one hole per Moiré cell, we're going to have mott insulator. And this is reported by these literatures. And if we dope the 2 holes per Moiré cell, we will get Moiré band insulator. And then we fabricate our device, which is very similar to our trilayer WS device, just with extra perturbation layer beneath the trilayer WSe2, which is a monolayer WS2. So it's a 4-layer structure. And then we measure the reflection contrast, and we take second derivative, we can get this result. And in this case, at zero field, gamma value of the trilayer WSe2 is higher than K values. So if we dope the system, we dope gamma value. And if we look at this red box, we zoom in and we take integrated intensity, we can see that many large dips, and they're corresponding to different filling factor. And this filling factor 1 is corresponding to gamma Moiré mod insulator. So there is a problem. Actually, we don't know the real location of each gamma Moiré holes. And so this is only a schematic. For the real locations, we need further study. And then if we apply strong electric field, we just lift up this K-valley. And at this case, we just dope the K-valleys, and they're corresponding to different filling factors, which are very obvious here. And this filling factor 1 is corresponding to K Moray mode insulator. So we just achieve that the switching between the K-valley and gamma valley Moray mode insulators. So in the summary, we just in the first part we achieved that field switchable KK and K gamma exciton polarons in trilayer WSe2. So the information are included in this picture. So we can see that as strong electric field, the K value will be higher, and the small field, the K value is lower. So this is the main idea to achieve the field switchable exciton polarons. And in the second part, we achieved that the field switchable K and gamma valley mod insulators in trilayer WSe2 Moray superlattice. So at zero field, the Moray mod insulators are formed by gamma holes, and at strong field, they're formed by K holes. Okay, that's all of my talk. Thank you very much.